so we also try to really put some ideas in a
live right now.
Okay, so we are in YouTube. So finally, Luis, you wanted to say something.
Of your talk, I wanted to ask something, and also like trying to present a theoretical representation of your results or understanding. Is there a way of measuring the strength of the two contributions of your potential, like the repulsive part, which comes from electrostatic charge, and also the attractive contribution? There is a way to estimate the ratio of the strength of the two contributions experimentally, I mean?
In principle, yes. I mean, if you follow what we did in the second part and go through the steps, then you essentially by shifting your vertical axis or the temperature axis, you essentially get the attraction strength. And by shifting the horizontal axis, so the phi axis, you essentially get this repulsive part of the potential, which then goes into this effective hardcore interaction. And then in the last step, you get the B2. The question, of course, is with what accuracy you get this, because of course the lines are. I mean, if you look with your eye, that's what we do so far. I mean, now we are thinking about doing this a bit more precise to get these data with more precision. But in principle, we get this out. Yes.
Okay. Thank you very much. I will come all the day with more questions. But thank you very much.
Okay. No, then we should discuss this.
Yeah, of course.
Thank you, guys.
Nice seeing you.
Yeah. Schön, dich wieder zu sehen auch.
So we move to our next talk. So, and the speaker is Marco Laurati. I think that in principle, Marco doesn't need any kind of presentation, but let me briefly tell you that he is also an experimentalist. So he's interested also in glass transitions, and he spent a few years as a faculty member of the University of Guanajuato. So, and also Marco has collaborated a lot with Magdaleno. So Marco, thank you very much for accepting this invitation, and you can start your presentation.
Thank you very much, Ramon. So let me first share my screen.
Okay. So we can see it.
Can you see?
Yes, we can see your presentation.
Okay, so first of all, I would like to say that I'm really honored to be part of this Magdalenos Fest, and I should actually thank the organizers for giving me the opportunity to contribute to this very nice event. And so, as you see, I was calling my talk with a sort of strange title, so a history of glassy friends. Well, about glassy, I think you can imagine that this is because essentially most of my collaboration with Magdaleno in principle, but also a lot of my research has been devoted to the study of indeed glassy states. So that's why. But actually, I have to say that this basically was the opportunity to really develop a very, very good friendship with Magdaleno, and also, of course, with many other people in Mexico. Friendship, which for me, it's really precious, like this Murano glass that you can see in this first slide of my talk. So the term history is related to the fact that I would like to present you today, let's say, things in a sort of historical order, starting from indeed the time when I first met Magdaleno. Actually, different from Stefan, I can remember exactly the first time that I met actually Magdaleno. So, okay. So actually the first contact with him, I remember very well, was in the beautiful city of Barcelona. We were both participating in this very nice conference, this international meeting on relaxations in complex systems. And I remember that during a coffee break in the conference, I think it was with Stefan, indeed, and suddenly Magdalena was approaching us, and then I wanted to introduce myself. As I said, I didn't meet him before, so I came to him and I think I said, yeah, you know, I'm Laurati, nice to meet you. And as it happens to many of us, the first time that you meet somebody, the reaction of Magdalena was something like this one, actually. But so actually, this is a joke. I mean, it's actually good. Actually, I was really surprised that he was really aware of what I was doing, and so actually we started to discuss about, of course, our scientific interests. And actually, this was sort of natural, I would say, because we had both a common interest, I think, at least, I mean, at that time, which was the study, indeed, of binary colloidal mixtures. So here I'm showing you just an example of 3D confocal microscopy reconstruction of one of these binary colloidal mixtures, which in this case is made of PMMA colloids. Well, two parameters that are typically used to characterize the colloidal mixtures are the size ratio. So in this case, the ratio of the radius of the small spheres compared to the radius of the large spheres, and the total volume fraction of the system. Of course, we both were interested mainly in the concentrated dispersions of these colloidal mixtures. Well, this because of several things. Let's say, at least from my experimental point of view, one of the interests was related to the fact that a binary colloidal mixture is the simplest multi-component colloidal system that you can study. So it's like sort of the hydrogen atom, no, for multi-component colloidal systems. It has also some interest in applications because indeed mixing two different species can be used, for example, to increase the packing ability of the system, so to pack more material essentially, but also, as we will see in the rest, at least in the first part of my talk, to induce also changes in the state of these highly packed systems, changes, for example, from solid to fluid that, of course, you can use to, for example, for transport purposes. No, so it's an important application scenario. And of course, this was probably the most interesting part for me and Magdaleno. Binary systems also provide, let's say, an enriched scenario for the glass transition, which, as I said, was one of our main interests. So then I was aware already, of course, at that time of the very important work of Magdaleno in the field. In particular, there was this very interesting paper from Maldonado and Magdaleno, which was describing essentially the phase behavior of these concentrated colloidal mixtures. And the main things that I would say the paper was showing is that indeed by mixing these hard sphere colloids, having increasingly different disparate, increasingly different sizes, sorry, has the effect of essentially expanding the fluid region of the system. So essentially it shifts, the characteristic volume fraction of the glass transition to typically larger values at sort of intermediate mixing. But actually even more interesting is what happens when you come to large size asymmetries, where effectively you can distinguish between different kinds of glasses. So you can distinguish, for example, between a double glass state, in which essentially both components are indeed dynamically arrested, and instead a single glass state in which one of the components, typically, of course, the smallest component, remains mobile while the large component is frozen. So actually, at that time, we were mostly interested from our experimental side on investigating the rheological properties of these glassy binary mixtures. And therefore, one of the studies that we did actually at that time was indeed investigating essentially along a line in which we kept essentially the total volume fraction of the system constant, and we increased the amount of small spheres in the system. So studying how effectively the rheological properties were changing. And of course, this gave us already signatures of what happens, obviously, in the phase behavior of these systems. So as you can see here, the signatures that we could see were evident in, for example, the storage modulus of the mixtures, but also the yield strain and the yield stress of our systems. As you can see, for a large size ratio of 0.2, so where the big particles are 5 times larger than the small particles, we could see that there is clearly a minimum in all these three quantities at a certain intermediate ratio. So which is, of course, an indication of a transition, at least from a glass state to a more fluid state, which is, of course, consistent with the expectation of the theory that Magdalena was developing. And actually, we saw also some dynamical signatures of this transition in the system at rest, essentially, where we saw that basically when you increase the amount of small spheres, essentially the localization, so the dynamics of the large particles in this case, show essentially a transition in the localization, which is a manifestation of the transition from being caged by large spheres to being caged essentially by small spheres. And in the transition, basically, we see the fluidization indeed of the system. And actually, we were also studying, seeing signatures of these transitions also in interesting studies that we did on the dynamics when the system is essentially under flow, so where indeed through the rheological field, so to the flow field, we induced essentially a melting of the system. So what we saw interestingly was that the system from being arrested was going to the flowing diffusive state through indeed a transient super diffusion, and also actually there was an interesting effect that we could see that the equilibrium, let's say the steady state localization of the system in the quiescent state was becoming smaller under shear, which indicates essentially a cage compression effect. Actually, these were two nice works of Tatiana, which also contributed a lot together with Stefan, indeed, to this work. But as you can see, these were signatures of something happening actually in the phase behavior, in the state diagram, but we didn't have a very detailed information on the precise effects of these transitions, especially on the dynamics of the system. And so this is what we did later, and actually I have to say that I was not so as polite as Stefan, and I was thinking of presenting this common work today. Well, actually I have to say that I was asking at least Stefan and Thomas before doing that. But essentially, so this is a work that indeed we took actually some time, also because it was involving a lot of people, as Stefan was already mentioning, but this was because it's a study that is combining different experimental simulation and theoretical results, which we're going to essentially assess effectively the dynamics of both the colloidal species in the mixture, while approaching effectively the fluid to single glass transition and the fluid to double glass transition in the system that I already mentioned in the previous slides, which is this mixture where the size asymmetry is basically 1 to 5 between the small particles and the large particles. So from our experimental point of view, the study of largely asymmetric mixtures, actually of both components, required the use of, let's say, a relatively novel technique, which is what is called indeed differential dynamical microscopy, in short DDM, which has essentially two very good, I would say, advantages compared to other techniques. One is that it's a correlation technique, so essentially it allows us, and it's also, sorry, in the reciprocal space. So basically it allows us to determine the Q-dependence, let's say, of the dynamics of the species, which, as you will see in the following, is essential in distinguishing basically the transitions. The second thing is that it's not limited like, for example, particle tracking by the spatial and temporal resolution of the instrument, at least not as much. Another very interesting thing is that we can use fluorescence, which allows us to easily essentially distinguish the two species involved, a thing which of course will not be possible, for example, with dynamic light scattering. So the technique works as in this way. So one takes, like in a normal microscopy particle tracking experiment, a temporal series of images. And then one takes, for example, two images separated by delay time delta t, makes the Fourier transform of the images, takes the difference, which has the advantage of removing any static, essentially, background from the process, and then makes the correlation and obtains effectively a power spectrum, which is a function of Q and, of course, the delta t. And this is actually two-dimensional, but by taking the azimuthal average, we obtain this correlation function here. from which we can extract essentially the intermediate scattering function, which is what could be also calculated by the theory and also through the simulations. Okay, so actually, indeed, I'm starting to show you some results of the theory and the simulations. So the first thing that we did was investigating the fluids to single glass transition along a line where essentially we're increasing the fraction of large spheres at constant small spheres. And so here you see basically the self-intermediate scattering function, so which tells us about the self-dynamics, so the dynamics essentially of individual particles, and instead the intermediate scattering function, which tells us about the collective dynamics instead of essentially a group of particles, so which reflect also the structure of the system. And what you can see while essentially approaching the single glass transition is that, well, the dynamics of both species tend to slow down, but the dynamics of the large particles, indeed, when we come close to the glass transition, they slow down much more than those of the large particles. So there is sort of clear decoupling between these dynamics. While when we look at the collective dynamics, we can see that instead, while approaching this transition, the dynamics of the two species, as you can see, become more and more coupled, so which means that essentially the small particles follow the slow relaxation of the large particles in the system. And actually, we could see, well, the theory, of course, reproduces that also on a line where essentially the amount of small particles was slightly different, slightly smaller, and we could get at least, even though a bit limited by the time interval accessible in the experiments, a qualitative indication of the same behavior also in the DDM experiments. So what happens then when we instead move to investigating the transition from the fluid to the double glass? So here I was putting again the previous transition as a reference. If you look now at the fluid to double glass, you can see clearly a very pronounced qualitative difference, no? Because now you see that essentially the slowdown of the dynamics while approaching the double glass transition is qualitatively very similar. Also, the degree of slowdown between the small and the large particles in the self dynamics. So essentially, of course, the small particles are still faster than the large particles, but essentially they slow down in a qualitatively similar way, basically. And in the collective dynamics, we can still see the coupling, which actually you see even much stronger in the case of the fluid to double glass transition, because when we are really close to the transition, the dynamics are essentially identical. And this was also in this case, I would say, nicely shown by the DDM experiments. And again, the lines are slightly different, but essentially the qualitative behavior it's clearly reproduced by all techniques. And so one can compare a bit more quantitatively the two transitions, both in terms of the self-dynamics and the collective dynamics. So in terms of the self-dynamics, this was done by looking at the relaxation time of the correlators as a function of indeed the increasing basically total volume fraction of the system. And well, you can see clearly, that when we approach essentially the transition at the largest packing fractions, the decoupling essentially of the slowdown between the large and small particles is much more pronounced indeed in the fluid to single class as compared to the fluid to the double class. So there is a clear quantitative and qualitative difference. But also there is a difference in the collective dynamics, which is revealed in this case by the Q dependence. So essentially, you can see that at the small Q values, essentially there is essentially the coupling, which is also, of course, related to the variation of the structure factor of the system, but at large Q values, where essentially we explore small length scales, which correspond, of course, for the small particles to the free volume inside the glassy matrix of the large particles in the single glass, then we can see in this case, even in the collective dynamics, more pronounced decoupling in the fluid to single glass than compared to the fluid to double glass transition. So, and similarly, one sees also this sort of decoupling indeed in the non-ergodicity parameters, especially in the fluid to single glass transition. Essentially, one sees that beyond the first structure factor peak, indeed, the non-ergodicity parameters of the small spheres start to lose their relation with the structure, basically, of the large particles matrix. So with this, well, a few remarks on this study, which I think was the first really thorough confirmation of the prediction of the self-consistent generalized Langevin equation theory developed by Magdalena's group. And I think it was, our study shows actually that there are indeed quantitative and qualitative differences in the transition towards these two different class states of the system, which can only be revealed if effectively one can investigate selectively the dynamics of each one of the species in the system. And also the study revealed that the Q dependence of the dynamics is also essential to distinguish between the transitions. So with this, I would like to make now a short break before telling you a bit more about the collaboration with Magdalena. So coming back then, actually to the first time that I was, sorry, I forgot this. I just wanted to briefly mention that we recently did also another study where in this case, by particle tracking, we could again verify and compare the dynamical transition of the small particles with respect to the NE-SCGLE state diagram. But then let me go back indeed to what I was saying, that I would like to go back to the first time that I was visiting Mexico, which was about 1.5 years after I first met Magdalena. And that was also very interesting event at which I was invited, which was this first international workshop on matter out of equilibrium, which was taking place in San Luis Potosí, the beautiful city of San Luis. And so I would like to share with you a very short anecdote about my participation in this workshop. So actually, at the end of the conference, I was going to move to Guanajuato to also visit the University of Guanajuato. But before going there, Magdalena was indeed inviting me to have lunch with him and with some other participants. But actually, after the lunch, I had basically to take the bus to go to Guanajuato. And unfortunately, the lunch was taking a bit longer than expected. Then I was thinking of taking a taxi, but then Magdalena was offering to give me a ride essentially to the bus station, which I think on one side tells you really about Magdalena, so how Magdalena is, so a very distinguished professor like Magdalena, which is just so simple and so open to offer you to just give you a ride to the bus station. But actually, the thing is that I was a bit afraid because it was already a bit late, and then I was thinking I would not be able to catch my bus. But then I didn't know of one of the other skills of Magdalena, which is that he can switch on the fast and furious mode when he's driving. So actually, I was able to come even a few minutes before my bus was actually going to leave. So I have to thank Magdalena for this precious skill because it was really good. So thank you again. And well, after this short digression, so I would like to say also that this was just the beginning of a very fruitful collaboration, which, well, actually, Magdalena was involving me in a lot of projects, of course, together with Ramon, the most important, which was, of course, the LANINFE lab, but also other projects. And I have to say that this for me was really, really important because it gave me the opportunity of starting to develop the soft matter lab at the University of Guanajuato and acquiring, for example, equipment and so on. So I would say that the contribution of Magdalena to my career was really, really important. And actually, this indeed it's an old picture of the first members of the lab, of course, again, together with Ramon. And now I have to say that the lab is in very good hands because it's directed by Eric Sarmiento. So I'm sure that it will be a very successful lab. So now I would like, in what is left, to quickly tell you also about another piece of the collaboration with Magdalena, which is on a slightly different topic, of course, still on the glass transition, but this time focusing on soft colloids. So this is a work that we did a few years ago, which is in this paper in soft matter, and which involves also people from the group of Magdalena, like Pedro Ramirez, and the very important contribution also of Edilio Lazaro and Patricia, of course. So actually, we studied the classical microgel system, so NIPAM microgels, which are these essentially thermally responsive particles, which undergo hydrophilic to hydrophobic transition when you increase the temperature of the system, and this transition, of course, induces a shrinking of the particle size, which has been used among, of course, other applications. For example, in something like drug delivery, it's a mechanism that you can use for releasing things that are trapped inside the particle at smaller temperatures. When you increase the temperature. So here you see, a couple of microscopy pictures of the particles that we were using. So in the swollen state, and then of course, in the swollen state. And here you can see effectively the measured deswelling transition in the size of the particles as a function of the temperature for our system. So as you know, I mean, these systems, this transition depends on a lot of parameters, the degree of cross-linking, but also actually the synthesis in itself can change a lot the internal structure of these particles, and this has important effects. So actually the glass transition, so the vitrification of microgel dispersions has been investigated also by others. For example, it has been studied in this work from the group of Peter Schuttenberger, where actually they used temperature changes to induce the glass transition. So essentially, starting from the deswollen state, if you rapidly quench the system to smaller temperatures, of course, you induce a change in the radius, and this change can lead to the dynamic arrest corresponding, of course, to the increase of the actual packing fraction. So they were able to see these glass states. And actually, recent works from people in Montpellier also showed some interesting things, like the fact that at least for some of the microgels, the transition actually shares common behavior with also harder system like the PMMA, at least until you enter into the glass state. For larger values, actually, so when you enter really into the glass, there are differences, especially in the aging behavior, which it's really peculiar in the soft systems, and it's related in part to the fact that you have soft particles which can release stress when they are compressed, basically, against each other. So actually, one question that we thought was not really addressed in the literature is the fact that indeed with the soft systems you can follow different routes to the vitrification, to the glass state. The one that we already mentioned, which is the change in temperature, which corresponds to a sudden change in the volume fraction. But of course, you can do also what you do with, for example, hard spheres. So keep the temperature constant and increase instead the number density of the system. And so the question that we wanted to address was whether the glass states that you form following one or the other routes effectively have the same properties. So essentially, if you find basically the same glass state. So for this, we did on our side confocal microscopy experiments and particle tracking, in this case, essentially in plane into 2 dimensions. And from the particle tracking experiments, we first investigated the transition at the temperature of 25 degrees and increasing the number density of the particles from small value into the fluid state, essentially to a value into the glass state. And we could calculate the pair distribution function, which shows what you would expect, so that the maximum of the G of R is shifting to smaller values while increasing the packing, and also the peak, of course, grows. And in the dynamics, we could see the classical slowdown of the dynamics until essentially we reach the dynamical arrest in this case. And similar features were found in the theory by Magdaleno following a similar, essentially, compression route. Then we did the following experiment. So starting from the state that was reached through the concentration route, we were increasing the temperature to 30 degrees to reduce the packing fraction and therefore melt the system. And in this, as you see, at 30 degrees now the pair distribution function moves to the right, and also the peak becomes smaller, and the dynamics, of course, become much faster. They are not entirely maybe diffused, but almost, I would say, diffused. And then from this state, we decreased again the temperature down to 25 degrees. And as you can see, both in the structure and in the dynamics, we could observe an hysteresis. So essentially, doing steps of finite time at each temperature, we don't go back to the same route, but the system goes back to different route with less structured system and with which shows faster dynamics. And the route, even if you compare the routes essentially at equivalent packing fractions through the concentration route or through the variation of the temperature, indeed you see that they follow different paths. So then we did a similar protocol again with in the theory, and actually what we saw is that of course we could induce the melting of the system, but the hysteresis in the theory, there was a bit of hysteresis, but was not as pronounced as in the experiment. But then we thought that this might be associated to the initial state of the system before the melting. So essentially, we then were compared our experiments with the theory, and indeed what we compared in this first graph is essentially systems in which the experimental aging was effectively considerably much longer than the theoretical aging. And so to check that, we in the theory they were also preparing a system with a longer aging, and indeed it was found, as you see, that if the initial system has a longer aging, effectively the hysteresis is more pronounced as effectively in the experimental system. And this in the theory, well, we could see now that this essentially depends on the fact that when you do a protocol in which you make the temperature changes in steps at fixed time, of course, what happens is that if the system is longer aged, there are some intermediate steps in which effectively the system is not able to reach the steady state, essentially. So that's why you get this basically hysteresis in the system. But then another question that we asked ourselves was whether the difference between the glass formed by decreasing the temperature and the glass formed through the concentration route was again an effect essentially of different aging of the system. So what we did was then taking the glass formed through the temperature route and let it age for longer times and follow the evolution of the structure and the dynamics of the system as a function of this increasing aging. And we found, I would say, something interesting. So as you see, the dynamics of the system, so these red lines are essentially the values of the glass obtained through the concentration route. And as you can see, the dynamics effectively evolve in the experiments toward the same dynamics of the glass obtained in the other route. But the structure doesn't evolve, essentially. It remains, well, maybe there is this peak, but definitely it doesn't go to the structure of the other route. Which is actually one difference with the theory. So in the theory, instead, you see that both quantities are going at long aging times towards the same values. So this is an indication that this effect on the structure must be an effect of the details, I would say, of the soft particles. Probably it's an effect of what I was mentioning at the beginning of the internal structure of the soft particles, which at the end is a gel network. And it might be that essentially when you suddenly increase the size, so the volume fraction of the system, to the temperature change, in this sort of the structure of the liquid remains to some extent frozen in. And as you see, since the dynamics are slowing down more and more, of course, this is not favoring the evolution of the system. But okay, understanding this effect indeed needs still some additional experiments. And the last thing I want to show you is that the other thing that we did was then repeating the melting procedure and reformation of the glass a second time, basically. And what we found is that in this case, you can obtain effectively a reproducible glass state. So if you repeat the melting and reformation of the glass, effectively the state is reproducible both concerning the dynamics and the structure of the system, which so also of course in the theory, and which I think defines well-established rejuvenation protocols for these systems when you want to essentially reproduce a glass state, for example, without using other approaches like, for example, shear or well, I would say other things. I mean, mainly shear, I would say. So yeah, this essentially was the other result of our study. And so these were the conclusions. So essentially, we could find that these glass states, in terms of dynamics, following the two routes, become comparable at sufficiently long aging times, but there is in the experiments this structural difference, which is instead persisting also at long aging time, and that must be related to somehow the intrinsic softness, I would say, of the experimental system, probably the internal structure. And especially the other, I would say, significant result is that we can define this proper rejuvenation procedure. And so very finally, I would like to also thank Magdaleno and all the people in the group for the very exciting scientific discussions which were taking place basically anywhere and in any condition, I would say. So, well, this was also a thing that I really enjoyed. And finally, so happy 70th birthday, Magdaleno, and of course, I hope to welcome you soon in Florence. So, thank you.
Thank you very much, Marco. So we have time for a few questions.
May I ask another question?
Yes, go ahead, Jan, please.
So I have a little bit of a difficulty to understand how you can have a single glass if the size ratio is larger than about 1/9. So if the size ratio is less than 1/9, the small spheres will be able to move through the holes in between the big ones. So you can have a single glass where the big ones are fixed in space, so to speak, and the small ones can diffuse through the holes that are left in between the big ones. But now you find a single glass up to a size ratio of 0.4. So where the small ones cannot move through the holes between the big ones. So I don't understand in that case how you can have a single glass. There should be a large fraction of the small ones that should also be arrested at the same time that the big ones are arrested. But nevertheless, you see an intermediate scattering function for the small ones that really drops to 0, which says that all the small ones are still mobile. I mean, I don't understand that.
So sorry again. So do you refer to the size, because what I was showing is indeed the size ratio, basically 1 to 5, no? So the size ratio 0.2, which is
Yes,
what?
so that, but you also showed in the additional experiments a 0.4, for example. But I mean, even in the 0.2, the small ones cannot move between the space that is left by the big ones.
Well, but this is, I think, one other thing that has to be considered, apart of the fact that at some point we did actually in one of our works indeed an estimate of indeed the minimum delta value that indeed where this could happen, but
well, that is pure geometry, right? I mean,
but yes,
you
but
can calculate this ratio.
that we did not, so that was not, I mean, mentioned is that of course the big particles are essentially in a glass state, but they are not completely immobile. I mean, still, for example, at the volume fractions that we investigated here. So actually, it is also what we showed in another work, that essentially the very slow dynamics of the large particles are also able to allow basically at some point the small particles to diffuse even in this frozen matrix.
So you're saying that the big ones are not really in the glassy state. They are still mobile.
Well, I mean, it's, I mean, apart of the fact that here, of course, what I'm showing it's the approach of to the glass transition, no, effectively. So all these states, as you see, indeed are basically approaching, no, the.
But suppose that you do a simulation where the big ones are really arrested.
No, of
then,
course, yeah.
Then I think you should find a large fraction of the small ones that are at the same time arrested with a size ratio of 0.2.
Yeah, but this is indeed, I would say, what is found, though, as you can see also in the non-ergodicity parameters, no? Because indeed these are quite, for example, in the fluid to double glass, no, the ergodicity parameters are quite high, indeed, essentially.
But I would say here you have a single glass, they freeze at the same time, right?
Yeah.
So in the right figure, I see them freezing at the same time. I don't see a difference for the F for the small and big ones in the right figure. So how do you conclude from this that the small ones are still mobile?
No, well, I mean, in this case, sorry, indeed, this is the fluid to double glass. So sorry, indeed, in this case, of course, they are.
Oh yeah, so I mean, yeah, of course. Yeah.
Yes.
But in the in the left figure, you find the same thing.
The left figure, you see that small length scales, basically the non-ergodicity parameter of the small particles, indeed, it's considerably lower, and it doesn't follow any longer the large structure factor 1, basically.
Okay, I have to think about it.
Mostly, of course, local dynamics. I would say, because you see it basically at length scales, which is beyond the first structure factor peak.
Yeah. And so around the peak, they are still both mobile or so immobile, right?
Well, yeah, I mean, well, if you look at the correlators, of course, the dynamics of because these are indeed essentially at the peak. So the dynamics of the small spheres, of course, are much faster than the dynamics of, as it's natural, the dynamics of the large spheres. But okay, they show also, of course, slow down. Yes.
I have to think about it. So thanks.
Yeah.
Okay. So Gerhard, please.
Yeah, can you hear me?
Yes.
Yes.
Yeah. First of all, Marco, thank you for this very interesting talk. Really learned a lot about it. I recall that in 1999, we wrote a paper that's Johan Bergenholz, Adolfo Banchio, and I, where we used mode coupling theory for a binary hard-sphere mixture with precisely the size ratio of 0.2, which was, of course, triggered by the study of Jan and Arnold Imhoff on this type of hard-sphere mixtures, where we also found from standard mode coupling theory, two-stage vitrification. So first the big particles formed the glass and the small particles were still mobile in a sense. And then eventually both big and small particles formed the glass together at a total volume fraction of about 0.253 or so. Now that brings me to my question, which actually I would like to pose also to Magdaleno, and it's a pity also to Thomas if he would be there. Actually, I heard that in the meantime, a comparison has been made between the predictions of the self-consistent generalized Langevin equation theory by Magdaleno and standard mode coupling theory represented by Thomas, so to speak. Now, regarding this type of hard sphere, asymmetric hard sphere systems, let me ask the question a bit strong way. Which of the two theories agrees better with the experimental data, and why? Can you?
Well, yes. No, I mean maybe before I leave the word to Magdaleno and Thomas, just to mention that here, of course, I was focusing on the comparison to the theory of Magdaleno, but of course, during the years, we also compared to the mode coupling theory predictions. We have a few words also on that.
Yeah. I mean, the theory of Magdaleno is so much easier to use, right, than standard mode coupling theory. So it would be really interesting. So what's the status of the comparison between the two theories and the experiment for this case of asymmetric hard sphere mixture? Can one give us a general statement? Which theory is better, or in a sense, which one is worse, and how do they compare with the experimental data?
You want to see blood, huh?
Sorry, Magdaleno, for asking that question.
So, Marco, if you agree, maybe Magdaleno could say something. That's okay for you?
Yeah, sure. No, that's what I meant. Yeah, I was.
Okay, Magdaleno, go ahead, please.
Okay, I think that mostly qualitatively, both theories say basically the same. There are some differences more in the detail that I don't think that really you can say this is better than the other one. Okay, but Luis wants to say something, and he has thought about that much better than I. But before I give you, I wanted to say something with respect to Jan Don's question with respect to the delta threshold. To see if I understood the conversation. Delta, you claim, Jan, that for delta smaller than 1, you might have the single glass, but the threshold is 0.1. Now, our theory predicts that threshold is about 0.4. Now, the value of this threshold really depends on how you do the calculation. You imagine that you have a certain concentration of big ones with a certain size, and then you put them fixed and see what is the window through which the largest particle could go through. But that depends on the concentration. If you say close packing, random close packing, like phi of the big ones, 0.6, it may be that you will have some threshold that small. But at the glass transition, with a packing fraction of big ones of about 0.58, this threshold is about 0.4. Am I going in the right direction with respect to what you asked, Jan?
Magdaleno, 0.58 versus 0.52. Standard mode coupling theory predicts 0.52, and then one argues in terms of reduced quantities. What do you get from your theory for
Yeah,
one component?
No, what happens is that mode coupling theory gives you 0.52 if you use Perkus-Jevic and without Verlet-Weiss. If you use Verlet-Weiss, then you go to 0.54. And if you do rescaling, it will give you whatever you want.
Without rescaling.
Yeah. But our theory has built-in a rescaling with a certain. So we simply adjusted to the simulation value. So there is not a prediction; is really a calibration, right? And now, if you calculate this threshold for the theory calibrated this way, then you get the value for this threshold now in mixtures of about 0.4. And I'm wondering, let's say that if the value was 0.64, then I would get the different value that it may be that I've never done that calculation, but I'm wondering if that 0.1 that Jan was talking about really comes from, it depends on this value of the packing of the big ones.
Thank you.
Guys,
can I ask, sorry, another question? Sorry for it's related to the thermosensitive class, to Marco. Where does this tremendous differences in the absolute waiting times come from, which you see between theory and your experiments?
No,
Do you have an idea?
actually, I mean, this was just, by design, basically. So, I mean, that's what I was showing, that essentially, at the beginning, basically, we thought that the waiting time, so the aging in the theory of 10 to the 3 essentially was sufficiently long, but actually this was not still long enough. And when we considered longer aging times, then the results become comparable, I would say.
Okay, guys, we have to continue with the program, but just briefly, Luis wants to say something, and after Luis, Stefan, and we close Marco's participation. Okay?
Okay. I'm not sure whether I can respond to two questions so briefly, but in order to contribute to Jan's question, I think one of the attributes of this paper is showing that, and I think there is a confusion here in terms of which kind of quantities should I discuss this single glass. And first of all, something is to discuss the behavior of the collective quantities, which indeed, as Jan pointed out, both of them look glassy, but precisely the point of the paper, and that was the picture that was presented by Marco, it's that you distinguish this single glass in the self-dynamics, not in the collective one. And this is what, I mean, it was missing the part of the collective dynamics in the simulations and theory. And I think this is an important point, also related to Gerhard's question. What is the difference in both theories? I mean, in terms of the kind of equations that you derive, none. In terms of the way you derive the equations, of course, there are different approaches or whatever. We actually recently published a paper with Thomas and I, discussing this kind of general properties of the theories, deriving essentially the same scaling laws, or let's say that you can derive from the theory. But concerning to the description of glassy systems on mixtures and so on, there is a crucial difference, because this effect on the self-dynamics, you cannot see it on mode coupling theory because of the way you do not couple the memory kernels and so on. There is this discussion, and then you don't see this effect that appears in the simulations. And this is more or less, this points in the direction of, okay, then our approach it's better or whatever. But if you, for instance, consider ultra soft systems, then MCT predicts a very interesting decoupling effect between collective and self-dynamics, which, because of the way you construct the self-consistent approach of Langevin theory and so on, you cannot see that thing because both memory kernels are, let's say, attached to each other. But in mixtures, since you are dealing with matrices and so on, you can see this decoupling effect, which is observed in the simulations. And I think we can discuss this, Jan, if you are interested later, because it's already too late. But I think I can answer your questions regarding whether the big particles actually, let's say, if you look at the collective dynamics, the trapping of the, let's say, the sea of glassy big particles, of course, collectively arrest the small ones, but not in the self-dynamics. And I think this is the essence of the question, but we can discuss that later. Thanks.
Thank you, Luis.
Okay,
Stefan?
I had a rather technical question to Marco, actually. So thank you very much for a very nice talk, Marco. I was just wondering, you were mentioning this was changing the size, and you were also saying about the internal structure and the softness and so on. So how much do the interactions actually change if you go kind of the different pathways you were showing?
Yeah, that's, I mean, this, unfortunately, it's something that we did not quantify, I would say. I mean, not directly. I mean, of course, you can see the difference basically in the resulting structure, no? But I mean, there are other effects indeed that might also come into play, especially when you change the, I mean, of course, this system has also some charging, I mean, not very pronounced, but there are also some effects of charge. And this, especially in the temperature route, may change depending on the temperature. So, of course, this might lead to a change in the interaction with respect to the concentration route.
Okay.
But this is something, yes, that we need to investigate also, because, you know, I mean, this depends also, all these effects depend a lot on the effective internal structure. So if our particles, for example, were basically homogeneous in terms of the degree of cross-linking, while in many other studies, they have a denser core and then a lesser dense core.
And also different cross-links, which then might affect.
Exactly.
Okay, thank you.
Okay, thank you very much, Marco, for the interesting talk and also for the memes. Hopefully you can send them.
Yes.
Okay, so thank you very much, Marco. Okay, so now we close this morning session, or at least this Mexican morning session. So thank you, Stefan and Marco. And I think that Cristina is going to close the presentation in